Postdoctoral fellow at the Jet Propulsion Laboratory. I also spend my time at the NASA Exoplanet Science Institute in Pasadena, California. I think this is a really big room. It's great that so many people are excited about the solar neighborhood and what we can do to be more complete in our efforts. Today I'll be talking about some of the work that I and my wonderful collaborators listed here have done to study the role of stellar multiplicity on nearby M dwarfs. So let's jump right in. So while the sun is rather average in many ways, it is unique in one way in particular, somewhat unique. The sun is lonely. We have only one star in our solar system, and all of the planets orbit the same star. But we now know that half of sun-like stars are multiples, and this stellar multiplicity rate increases to 80% or higher for the most massive O-type stars. It also decreases with decreasing mass to about a quarter for the M dwarfs. So when we ignore the unsun-like binary stars, we ignore half of the picture. This is particularly egregious when we consider the planets of these multi-star systems. I do not have to convince this crowd that it is comparatively easy to detect planets around M dwarfs, but I may, however, need to convince you that we need to be studying the stellar companions to M dwarfs, so I will attempt to do that here. Stellar companions affect planets from the very beginning. We know that companions can impact planet formation by perturbing and truncating protoplanetary disks, gravitationally exciting planetesimals, and scattering or ejecting planets that have formed. We also know that once the planets have formed, stellar companions can inhibit planet detections. This is true for radial velocity detections, as shown by Ortiz et al. 2016. It's also true for transit detections, as shown by Lester et al. 2021. This figure shows that transiting planets are detectable at all periods within both single and multi-star systems. However, in the binary systems, transiting planets are not detected unless they're larger than about 2 Earth radii. So this poses a huge problem for finding transiting Earth-sized planets in multi-star systems. Stellar companions can also affect our ability to characterize any planets in the systems once they've been detected, since the companions can contaminate the light curves of transiting exoplanets. This can lead to underestimated planet radii, skewed planet radius distributions and occurrence rates, incorrect characterization of both stars' properties, and improper mean density and atmospheric values. This has major implications for our search for Earth 2.0. One might think they found a rocky Earth-sized planet, but once the light from the stellar companion is accounted for, they might instead find they have a gaseous sub-Neptune on their hands. It's therefore critical that we account for these stellar companions, but how can we do so most accurately? The long-term astrometric monitoring from Gaia has proven invaluable for diverse science cases such as stellar variability, the structure of the solar neighborhood and the Milky Way as a whole, and in the future, even exoplanet detection. It is also useful for identifying wide, common proper motion companions. However, it's been shown for the close-in binary companions that the relative motion of the pair disrupts Gaia's ability to provide us with an astrometric solution. Throughout our M-dwarf multiplicity survey that I will talk about in a moment, we detected companions to 151 of our targets, and the properties of these companions are plotted here. The majority of these, about 60%, were not resolved in Gaia DR3, and often did not even have an astrometric solution for their parallax or proper motions. So what can we use to detect and characterize the multi-star systems that are not resolved within Gaia? Well, Gaia metrics are one place to start. When metrics like the Rui and IPD FMP values are elevated, this can indicate that a source is likely non-single or otherwise extended. The Rui value is useful for identifying close-in companions, and the IPD FMP value is useful for identifying more widely separated companions. We did find that the majority of the unresolved companions had elevated values, but not everyone. In particular, these metrics were not as reliable for the faint late-type companions. And even though an elevated value can indicate the presence of an unseen companion, it doesn't actually give you any properties for that companion. So how can we obtain these properties? Unfortunately, the atmosphere is our enemy in this endeavor. Its hot and cold cells make the atmosphere turbulent, distorting the starlight from distant stars. Luckily, we can use speckle interferometry to fight back. Speckle imagers freeze out atmospheric interference, allowing us to resolve companions down to the diffraction limit of the telescope. Using speckle imagers at the Lowell Observatory and WIN telescopes, we have carried out the pervasive overview of companions of every M dwarf in our neighborhood, or Pokemon survey. The goal of the Pokemon survey was to provide a complete as possible census of M dwarfs through M9 out to 15 parsecs, though we also imaged a number of brighter M dwarfs at larger distances. In total, we observed 1,125 nearby M dwarfs at diffraction limited resolution, and we detected companions to 151 of them. 24 of these are newly resolved companions. Although these aforementioned companions were not resolved by Gaia, they were resolved in our speckle images. This demonstrates it's crucial to use high-resolution imaging in addition to astrometric monitoring in order to find and characterize stellar companions. I will note here that each detection technique fills a particular gap in parameter space. Here, speckle imaging is compared to a number of different companion identifying techniques. Speckle imaging is well suited to identifying companions from about 0.1 to 1 arc seconds, with magnitudes up to about delta magnitudes up to about 6 in the I band. In order to identify the population of companions that were not detectable in our images, we simulated the companions that could orbit each of the stars in our sample. For this, we used the Duchenne and Cross 2013 mass ratio and orbital period distributions. We then used the contrast curves from each of our speckle images to evaluate the sensitivity of each image to these simulated companions. Additionally, isochrone fitting allowed us to determine whether the companion was likely bound. We find that the majority of the simulated companions, more than 70%, were detectable within our speckle images. This is particularly true for the nearby targets. In general, the companions that were not detectable within our images were either very close in or much fainter than their primary stars. These results show that speckle imaging is highly reliable for finding and characterizing stellar companions. After taking into account additional companions known to the literature, we find a stellar multiplicity rate for the M dwarfs of 23.5 plus or minus 2%. This is consistent with other recent surveys of M dwarf multiplicity. And when we take into account the higher order multiples, we find a companion rate of 28.8 plus or minus 2.1%. So this tells us a lot about the M dwarf systems in our neighborhood, but we also want to relate all this back to the planets that these M stars are hosting. So as noted, it's been shown that for close-in stellar companions can inhibit planet formation. We therefore compared the projected separations of the planet-hosting Pokemon multiples to the non-planet hosting Pokemon multiples. I should note that these are as yet non-planet hosting. We'll likely find some someday. We find that the non-planet hosting multiples have a peak at 5.57 AU. This is consistent with what other M dwarf multiplicity surveys have found. However, the planet hosting multiples have a peak at 198 AU, a difference of more than an order of magnitude. Of course, we have far fewer planet hosting than non-planet hosting multiples in our system. But various statistical tests have shown that these two distributions are likely drawn from different parent distributions. This result represents statistically significant evidence for a correlation between binary separation and the presence of a planetary companion in M dwarf systems. Here, I want to briefly mention some future work that our team will be carrying out. As we heard this morning, in its most recent data release, Gaia has provided BP-RP spectra for hundreds of millions of stars. Using these spectra and data from 2MASS, we are homogeneously spectral typing all of the M dwarfs in our sample. This work will allow us to calculate the M dwarf multiplicity rate by spectral subtype through M9. And we will also present updated mass ratio and orbital period distributions that take into account even the lowest mass M dwarfs. Additionally, this Splinter is about being complete. So I will note that the Pokemon survey wasn't fully complete. The Pokemon sample was developed before Gaia data had been released. And an examination of Gaia DR3 indicates that there are additional late-type dwarfs that we have yet to image with our speckle imagers. And so we are therefore assembling the Pokemon Distance Limited Catalog, or Pokemon DLC. And we are going to be imaging these remaining M dwarfs with the Nessie speckle camera on the 3.5 meter WIN telescope. And so these observations, we hope, will be of fundamental utility to both stellar astrophysicists like you trying to study system architectures in the solar neighborhood, and also exoplanet scientists studying the planets in these systems. So in summary, multi-star systems are common, but we do not yet understand the frequency at which they host planets or what these planets are like. We do not fully understand how stellar companions shape the multi-star systems of the solar neighborhood. Speckle imaging allows us to reliably explore system architectures in these multi-star systems. And using speckle imaging, we've carried out various studies of M-dwarf multi-star systems in the solar neighborhood, a few of which can be found here. So thank you so much for your time, and I will take any questions.
And do you find any companions that are, so you're looking for fainter objects, but it could be compact objects also. Did you find any? Well, where's the nearest neutron star hiding? No, but because they should be like white dwarfs outnumber neutron star by a factor 50, and there's no neutron star within like did you find compact objects companion?
Well, we did not find any compact companions. I'm so sorry to disappoint.
I'm really excited about all the spectacle that's happening and how nice and close into the star it can reach down to. And I want more. So my question for you is when it's like immersed in this stuff, are there any like improvements that we might be able to expect in the next 10 years or decade? How the closest separation is safe to resolve or are we pretty much at the limit?
We are pretty much at the limit of what we can expect right now. You're pretty much limited by aperture at this point. And so if you want to get down to even closer systems, you have to explore other techniques that are limited by the diffraction limit.
All right, we got an online question. Can you please repeat this?
Oh, sorry. Yeah.
Isn't there a very strong bias in the binaries not hosting planets? Because binary stars are very much avoided by almost all planet surveys.
Yes. So the question was, isn't there a bias since most planet finding searches completely avoid the binaries? Yes. Exoplanet scientists have very much avoided the binaries. I could very much get on my soapbox about that. But we have tried, so all of almost all of the systems that we surveyed have been observed by TESS. As we saw from Katie Lester's paper, there is a bias against detecting transiting Earth-sized planets in binary systems. But these are systems that have been looked at with TESS. And so in theory, at least the larger planets and and planets at all periods would have been detected in these systems. And so we try to be as unbiased as possible, but we definitely need more data. We need to be finding more planets in multi-star systems in order to really beat down on these uncertainties and understand a bit better how the planet hosting multiples differ from the non-planet hosting multiples and single star systems.
Time for one more.
Whoa.
Thank you.
So if you want to go to really close separations, you have to go to spectroscopic binaries. Are all these stars also going to be looked at for that?
Yeah, so that is something that we're hoping to do as well with this work, using the Gaia BPRP spectra, as Zach talked about this morning. We're hoping to develop a Cannon model to search for additional unknown spectroscopic binaries within the sample that have yet to be detected.
Okay, let's thank our speaker again. Okay, begins. We have a online presenter.
There will be no technical issues. Adam guarantees it. So,
Is Mari online?
yeah, she's.
Okay. And Mari, I'm going to give you a 3-minute warning when you're.
Okay, thank you. I think the screen sharing needs to be enabled.
We're working on it.
Okay, thank you.
Time has not started yet. Don't worry.
Okay.
Okay, you're a co-host, so should you go ahead and try to share?
Okay, hopefully that's working.
We have it.
Perfect. Okay, I'll get started now then.